My name is Jiang, the team leader for Team 3863, and here we have my members, Ashley, Haris, Gavin, and Jinwei. Our project title is Deepfake Generation and Detection, supervised by Dr. Leong, and we'd also like to show our thanks to Mr. Chi Peng Xiang for allowing us to utilize his face for our generation datasets. So the objective of our project is to develop an easy-to-use method for the public in generating and detecting deepfakes, which does not require them to possess any technical expertise, while also providing performance. So for the detection models, we'll first start with the SVM model. Firstly, we have to import the necessary libraries and packages to be used. And next, we'll specify the folder paths that contains the images to be used for our training, testing, and validation datasets. Here's an example of what the images look like. So this is an image of Gal Gadot, which is not tampered with. And this is an image of Blackpink Rosé on Gal Gadot's face that is deepfake. So with all that, we'll combine them and split them into paths for the training, testing, and validation data sets. Next, we'll perform our pre-processing, and we'll first start off with the face detection and extraction, and followed by image augmentation. So here's an sample output of what the cropped out face image is, and this is the image after augmentation is performed on it. So that is performed for the training dataset, in which the testing and validation dataset will only undergo normalization. We'll then form a data frame out of those datasets for the training, testing, and validation. Next, we'll perform feature extraction to extract features from the dataset itself, and the output will then be passed for further pre-processing, namely feature scaling using standard scaler, as well as feature dimensionality reduction using principal component analysis, PCA. So our data is now ready for training and validation, but before that, we'll have to select the best parameters for our model itself. And we'll do so by using grid search, and the best parameter that gives us the highest accuracy on our testing dataset will then be used. So with that, the best parameters give us a 94.4% accuracy on the testing datasets, and on the validation dataset itself, it's got an accuracy of 94.2%, which is definitely outstanding. If you were to look at the true positive rate, is 0.99%, which is almost close to zero error.
Okay, thank you, Ziyang. So for the CNN model, right, all the users have to do is place all the real images within the folder here called real, and all the fake images within the folder called fake here, and key in the folder path here. And next, the program will actually resize the image by 256 by 256 and store it into a NumPy array. And once that has been completed, we'll actually pass it through the neural network. So what we do here is actually we have a VGG model in which it will actually use two convolutional layers followed by a pooling layer, and once again entering two convolutional layers before entering another pooling layer. And I added two more additional convolutional layers. So what these layers does is that for the convolutional layers, they actually extract out features from the images and actually create feature maps. Once that has been completed, it will actually flatten the image into a one-dimensional vector and pass it through the fully connected layers here. So these layers will actually make a prediction of the probability of being both fake and real, and the highest probability will be the final output. So over here, you can see actually for the starting first epoch, the accuracy is actually around 60%. However, running the neural network multiple times through several epochs, it actually achieved an accuracy of 99.3% on the training data set. And another architecture that we actually tried is actually the AlexNet architecture, in which the layers actually go by one convolutional and enter another pooling, once again, another convolutional, and once again, another pooling layer. I added 3 more additional convolutional layers to extract out more features from the image. And once again, I'm flattening the image and entering into the fully connected layers. Both models are actually using the SGD optimizer, in which I can actually adjust the decay and learning rate. And for the AlexNet model, you can see the accuracy for the first epoch is roughly around 50%. And as for towards the end of the training of 20 epochs, it actually scored an accuracy of 98.98%. And moving on, for the general public, for the detection aspect, all our models can be used for the general public using a simple to use process. So we have a separate notebook here just for the general public. All the users have to do is key in the folder path to the images they wish to predict, and there should be a folder called predict in there. And last but not least is the users actually have to load in the model here by keying the model path here. All they have to do is click on the run button here, and they will actually make a prediction. So over here, the model is actually doing the prediction and it's printed out right over here. The first image within the folder is actually a deepfake image, and the second image is actually a real image. And here's the output of either 1 or 0. And that's actually it for the detection aspect. And I'm passing my time over to the generation team now. Thank you so much.
The generation team, which consists of me, Ashley, Haris, and Gavin, will now be going through the generation notebooks that we have developed to generate our deepfake images. So the first thing one will need will be 2 sets of videos, the source video and the destination video, to generate these deepfake images. So in our case, our source video, which we'll be using, will be this video of Mr. G over here. Destination video will be this video of our groupmate Haris. By the end of this notebook, after we have executed every cell, we would obtain the deepfake image of Mr. G's face over the destination, which is Haris. So the first step to perform after both of these videos are within their respective directories is to obtain the frames within both the source and destination video, as you can see over here. After this is done, the face will be extracted from each of these frame images for both the source and destination videos. After this is performed, we will align and landmark both of the source and destination extracted facial images, as you can see over here, for both Mr. G and for Haris. After this is done, we will perform facial masking for the destination aligned images. Additionally, we offer the option to perform segmentation masking to remove any obstructions to the face as shown below. As you can see, Mr. G's fingers are removed from the mask. These facial masks will be used during the conversion phase of our notebook. Now we'll be going through the training phase.
Thanks, Ashley. We will then get the faces from the respective folders from the pre-processing phase, where SRC align is the source image and DST align is the destination image to put onto the source image. After that, we can initialize the model. For our deepfake generation process, we're using a variational autoencoder, where it uses a shared encoder and 2 decoders to generate a deepfake. For the original autoencoder, the optimizer we're using is Adam, and the loss function we're using is mean absolute error. We then compile the model, and you're able to see what takes place in the encoder and the decoders. So for the encoder, it makes use of convolutional layers, flattened layer, dense layer, and the upscale layer. And in the decoder, it makes use of upscale layers and a convolutional layer to reconstruct the image. The lightweight model that was developed on the other notebook also uses the same architecture as the original autoencoder, but it uses less convolutional and upscale layers. To make up for it, it uses a max pooling and upsampling layer. This model also uses less memory so that it can work on lower-end computers. However, the deepfakes it produces will not be as good as the original autoencoder model. Now I'll let Haris talk more about the training phase and the conversion process.
Thank you very much, Gavin. So firstly, training will begin by getting 2 batches of the same 16 images, where 1 batch will be processed and be applied through image augmentation, and nothing will happen to the second batch. So we'll then pass this set of images into the autoencoder for it to train with the function train on batch. So the algorithm will warp and morph the warped images to try and match the original images. So the model will here learn more about where to warp from each facial point, allowing it to reconstruct the facial features. So autoencoder A will be handling the source face, autoencoder B will be handling the destination face. So this allows the algorithm to plot facial features on the same areas of both faces to reconstruct the face layer to another person's face. So I'll repeat this step over numerous iterations. This is to ensure that the training data will iterate the entirety of the pre-processed dataset. So during training, our program also shows preview images based on the training progress of the model, as you can see over here. So once enough training has been done, we'll then move on to the conversion phase. So in the conversion phase, we'll be loading through the image from the destination outline folder to use as the base for the final deepfake. So you'll first get the crop image, which allows us to apply prediction on it. You'll then send this predicted face onto the next function to apply color correction and Gaussian blur. We also apply the landmarks from the mask to get the face mask. Finally, we will then apply Poisson blending and seamless clone with the face mask, the original destination image, and the landmarks to get our final output. So as you can see right here, we'll apply what the autoencoder learned from the source images on the left and put it on the destination images in the middle to get our final output on the right. So our output consists of many different poses of Mr. G's face deepfaked onto my face, Hari's face. So in addition to this data set, we also included another data set which includes my face as the source face, Ashley's face as the destination face, and the final output as you can see right there on the right. So we did this because we felt that our original data set was lacking in coloration and variation. So this resulted in better quality deepfake and much more better color variation. This is due to our second data set being a total around 4K images each. So we have come to the end for deepfake generation as well as the end of our total demonstration. So we hope you enjoy our demonstration. Thank you very much for watching.